Good day, students. Today, we want to talk on the topic titled Simple Idea of Circular Motion. It says that an object moving with a constant speed along a circular path is said to have a uniform circular motion. Let's see some example of circular motion. Okay, now an object moving with a constant speed along a circular path is said to have a uniform circular motion. Example of such motion are a stone tied to a string which is whirled in a horizontal or vertical circle. In a horizontal or vertical circle. You are whirling it round. That's a circular motion. Another one example, if you have to list some examples, another one is a satellite circling around the earth. A circular motion. Another one, the earth moving around the sun. So another example, the moon circling the earth, the planet moving around the sun. The examples of circular motion. Now let's see centripetal force. We use A, small letter A, to represent centripetal force. It is defined as the acceleration direct towards the center of a circular path. You can see acceleration directed towards the center of a circular path. When an object is moving around the circle like this, the force that keeps the object moving in the circle without skipping away, that keep it in that circular path is centripetal force. You can see this arrow says centripetal force, but the centrifugal force is opposite to the centripetal force. That's why if the value for the centripetal force is 2 Newton, the centrifugal force will be minus 2 Newton. You see, apply the same formula. The centripetal force is mv squared over r. Mv squared over r. We're still going to talk on that, but let's know that centripetal acceleration equals v squared over r, where v is the uniform velocity, r is the radius of the path. This radius of the path, this is the center of the circle. From the path where the object moves around the circle, the circumference to the center, that's the r, the radius of the circular path. Okay, it defined as centripetal acceleration is defined as the acceleration direct towards the center of a circular path. A equals v squared over r, where v is always directed along the tangent, you can see it, along the tangent to the circle at any point of the path. A is always directed towards the center of the circle. See, the acceleration is always directed, of the object is always directed toward the center of the circle. Don't forget A equals to v squared over r. You can see the velocity at which the object, this is the object. When it's moving, look at the tangent, the v, the velocity. When it gets to this point, the velocity at which it moves is the tangent to this circle moving object. You can see, please don't forget the formula A equals v squared over r under circular motion. Okay, the inwardly directed acceleration leads to a force known as centripetal force, which is also directed toward the center of the circle. I told you that our force equals to ma. We know that one before. Force equals to mass times acceleration. But under circular motion, your A equals v squared over r. When you replace it, you have m. Instead of writing A, you replace it with this v squared over r. That's why our centripetal force is mv squared over r. But when you are talking about centrifugal force, you only introduce negative when it is centrifugal force. Is that okay? Centripetal force is mv squared over r, where v squared over r is our centripetal acceleration, which is directed toward the center of the circle. Okay, the inwardly directed acceleration leads look at the arrow. That means that the acceleration is being directed toward the center. And the force that keeps the object moving in the circular path is the centripetal force. The inward directed acceleration leads to a force known as centripetal force, which is also directed toward the center of the circle. You can see, please look at it very well. Centripetal force, the force that keeps the object towards the center of the circle, while the centrifugal force is the opposite to the centripetal force. You can see the arrow directed outward, motion in a circle. Now let's see centripetal force. Centripetal force is defined as that inward force required to keep an object moving in a constant speed in a circular path. Okay, centripetal force Ft equals mv squared over r, where m is mass of the object moving in a uniform velocity v in a circular path of radius r. Ft equals ma, where a equals v squared over r. Now let's go to angular speed and velocity. We use W to represent angular speed. Okay. Consider the speed of a stone that is whirled on the end of a string. The stone moves in a circular path as shown below. You can see the stone being whirled around. P to Q is the distance at which the angle between the P and Q is theta. S is the distance between P and Q when you are whirling it round. Is that okay? We are picking the distance from P to Q, and the distance from the center of the circle to where the object is previously is R. When it moves at an angle a little bit forward, before it moves around the circle, when it moves this distance, S, you have the angle of movement to be theta. Okay, don't forget that our angular speed equals theta over t. What is theta? We call it angle turned through by the body. This is the angle at which the body turns over time taken. Don't forget this W, angular speed equals to theta over t. And the unit of angular turn through by the body, theta, is radian. The time is in seconds. Now, the unit of angular speed, W, is radian per second. If the unit here is radian and the down one is seconds, the unit will be of this angular speed will be radian per second. Take note. You can see it. The velocity is tangent to the circle. You can see the distance at which it moves, S, and your theta. From here now, don't forget that your theta now will be S, the distance S over R. Your theta is S over R, where W is theta over T. Is that okay? Please, they are very, very important formula in circular motion. Please, very take note of this. Very, very important. Okay. Now, suppose the stone moves from the point P to Q in t seconds, so that the radius OP sweeps through an angle theta in the same time, that is, angle POQ equals to theta. The angular velocity W of motion is defined by W equals theta over T. Now let's go to angular velocity. We have angular speed. We have done that. W. Now angular velocity. Now angular velocity is defined as the angle turned through divided by the elapsed time. You see, the two of them are the same representation, W, but the only thing is that angular velocity is a vector quantity, while angular speed is a scalar quantity, but they still have the same unit, radian per second, the way we have it under velocity and speed. Now, it is defined as the angle turned through by the body divided by the elapsed time. We can compare this with the corresponding definition of linear velocity given by, don't forget, linear velocity equals V equals S over T. Is that okay? Displacement over time, where S is the length of the arc PQ. Length of the arc PQ, that's the S, PQ. We can see from equation 1 that the magnitude of angular velocity W is defined in analogy with the ordinary linear velocity v. Instead of linear displacement, we use the angular displacement theta. Is that okay? We use, instead of linear displacement we know as a normal s, we now use angular displacement. We use this theta. That's why you see it here. Or use, anyways, have it theta over t. When you write velocity, normally velocity equals to displacement over time, but when you come to angular speed, angular velocity, you use w equals to theta over t. Is that okay? That's why you see theta over t. That's what we are saying here. Instead of linear displacement, which is s, we use the angular displacement theta, which is this. If angle theta is measured in radians, good, then it can be shown that theta equals s over t. S over r, sorry, theta is s over r. You cross multiply, you have s equals to r theta. Is that okay? Since you know that is our theta, angle turned through by the body is s over this r. That's why you have it, theta equals s over r. You cross multiply, you have s equals r theta. V now, as you know before, angular linear velocity. Linear velocity equals s, this linear displacement over time. And you know that your s equals r theta from here. You replace your s with r theta over t equals r multiplied by theta over t. What's our theta over t? Don't forget we have it as w. You replace it with w. We have v equals to rw. That is this radius multiplied by the angular velocity. It's a very important formula. V equals to rw. Thus, the linear velocity v is related to the angular velocity w by v equals rw. S is in meters, r is in meters, v is in meter per second, w angular velocity is in radian per second, and also angular speed is in radian per second. In the next class, we are going to go into calculation. We are going to stop here. Please subscribe to my channel so that you can have access to the latest video. Have a wonderful day.